Thank you so much. Yeah, I really appreciate IPAM for bringing us all together today. And today I'm going to talk about how to compile a little bit more deeply in the active volume architecture. I feel like this work has been anticipated for quite some time. I know PJ was looking into doing a similar thing at BenchQ for a little bit, so I'm proud to finally let this work see the light of day. So I split the talk up into 3 sections. I think the first one has been covered no less than 2 times in this conference so far. So I'm very happy to see that we're all thinking along the same lines. But I'm going to rehash it again in my own words. Then I'm going to talk a little bit about active volume. Unfortunately, I'm not going to go too much into the architecture because I want to focus on the 3rd section, which is just basically doing this deeper compilation that I was talking about before. OK, so without further ado, I will start off my talk, like all great scientific talks start, with an internet meme. The way that I think about resource estimation over the last close to 3 decades now is progressing sort of down what I call this QRE iceberg. And as we descend down the iceberg, let's say we pick a particular algorithm, it'll start with some gate complexity arguments, and then sort of go, hopefully, all the way down to a full implementation of your algorithm. And I've noticed over time that as we descend the iceberg, really 4 qualities tend to have been improved over time. One of them is the comparability of our resource estimates. Right, for instance, like you tell me a big O notation thing, I have no idea how to compare that to like a classical computer. I just think it's nice, so I decide to try to build a quantum computer to find out. The next thing is like the resources for your estimate tend to go down as you descend the iceberg. Previously we had less fleshed out things like T-state factories, and now we have much more efficient magic state cultivation techniques, which have decreased resources significantly. Another thing is like hardware specificity, right, where now we have, it's exciting, we have like specific architectures that we talk about, and Kevin can compare in each of these slides, which just like makes my heart sing. And the last one, I guess, is just like actual time for development, right? Like it takes time to make your way down the iceberg. Like physically, it took us like 30 years with like Shor's algorithm even to like make it to what I call basically depth 3 of the iceberg. OK, so yeah, so this first one I'm sure everyone is very familiar with. We have these gate complexity arguments, which is just like a by hand count. This bounds the number of operations in your circuit, and largely ignores like how each of those like black boxes are implemented. Right, this level is basically defined by oracles and black boxes and stuff that you just assume works. But papers like Shor's and Grover's were enough to inspire VCs to give us billions. So they've done their job. Next up, we have like NISQ gate counting. And this is the sort of resource estimate that I think I saw from Artur the other day, where he was sort of counting up these like 2-qubit gate estimates by hand still, and still compiling specific things. So these are things that are easily implementable, like even nowadays, which are definitely a step up from all these black boxes that we had before. And you'll also notice this last point, that often these resource estimates can be dominated by number of shots. It's possible for more fault-tolerant resource estimates to also have this property, but I think it's really a defining factor of these sort of NISQ type resource estimates. And yeah, here's just one of a billion papers you can find on this from way back in the day. Preskill and his group with Beckman decided to tackle this problem and try to reduce resource estimates for factoring. Next up, we have what I call depth 3, or just like gate counting with error correction. So in this step, you really talk about things like T gates, CCZ gates, and you're still just sort of like counting gates up and accounting for them by hand. But you're now taking into account some error correction strategy. And we're going to take a second to go through this like flow chart that I think everybody is using, but maybe hasn't really been put on a slide before. Apologies if the the font size here isn't enough. I'll try to dictate each one of these so that it's easily viewable to all of you. So you start with like, you guess an error correction strength, right? You guess a code distance that you have, right? And the first thing that I tend to do is like, have I seen this distance before? If I haven't, well, let's try it. Let's see if it works, right? So we calculate the qubit number given your error correction strategy that this particular distance affords you. And then you say, OK, is this memory sufficient? If no, then OK, maybe we want to decrease the error correction strength so that with the same number of physical qubits, we can get more logical qubits, hopefully enough to accommodate the particular application that you want to do. OK, so you go back to the beginning, you decrease your error correction strength, recalculate your qubit number. You find, in this case, you do have sufficient memory. Happy day. Now we can calculate our time to solution. This is basically just like explicitly counting your gates and taking into account the fact that things like your error correction strength can affect your cycle time or something like that. There's more than that can just happen. You have to sometimes change distillation strategies as well. But you can imagine that each time you set a distance, you have to calculate one of these time to solutions. I'll get your question in just a second. Then we figure out whether it's acceptable error probability. And if no, then, well, we got to try to increase error correction strength. But if we tried this distance before, we know it doesn't work. And so you fail. And you say, like, OK, QRE is failed. And maybe you have to increase the size of your computer to get a useful output. But if the total error probability of your circuit is acceptable, then you get like a success, and you can fully calculate the time to completion.
So yeah, because you have that right below corner, I would guess that you're fixing kind of a hypothetical device size here.
Yes.
So how do you do that in the first place?
Well, typically you pick a number of physical qubits if you're talking about a you call it a superconducting architecture or an ion trap architecture. But in photonics, usually we talk about having a number of single qubit, single photon generators. That usually is what defines the size of a photonic architecture. I hope that was clear enough.
Is it like an industry secret, or could you give me rough numbers of like what size of systems are you thinking and doing these kind of research systems?
Well, this can be applied at systems of any size, right? It can be applied in the early fault-tolerant era or at the fully fault-tolerant era. If you're trying to get me to spill the beans on how big PsiQuantum's machines are going to be, unfortunately, I'm going to have to decline the question. Any other questions before we move on? All right. So now I think we're getting sort of to the more of the bleeding edge of what science is thinking about. Oh, yeah. Here's some examples of what I call like a depth 3 resource estimate, right? Gidney, I think Gidney sort of pioneered this sort of method back in the late 2010s. OK. Next, we get to the stuff that's really, I think, the frontier of where we're at right now. And these like compilation pipelines that we heard from Kevin, Nariman, and a bunch of other amazing people at Rigetti have done similar work as well as 1QBit works in this regime, wherein you essentially schedule every darn gate in the circuit. You have like a full circuit of a fault-tolerant algorithm, and I want to figure out like where do I place each gate in the circuit. And that's what we're going to be talking about today. Specifically, I'm going to focus on when each gate is implemented and not talk about so much where each gate is implemented. So this basically allows us a bit of extra freedom to deal with whatever changes to our architecture might occur. OK. Oh, yeah, I should set this point as well. So remember at the beginning of our previous algorithm, you had to have a guess for your distance. So we often find that for depth 4 resource estimation, you want to use a depth 3 resource estimation to get that initial guess for your distance. Since every time you calculate the time, you're going to have to recompile, it can take a lot of time if you've got to recompile a lot. So getting a good guess using a distance 3 resource estimate is crucial in order to make this compile in a reasonable amount of time. And I think we find for our compilation pipeline, it's no more than like 3 or 4 recompilations are required before we find a distance that's like optimal for our application. So next up, I'm going to speculate on the future of what I hope to see. That's sort of like a full stack simulation. Basically, I would like to maybe in the next few years start thinking about planning out what exact electronic pulses are required to control something. allow for feedback that is dependent on decoding and stuff like that. And I feel like we will see a lot of the same patterns persist as we move further down the iceberg. And the last one is, just do it, right? Everybody wants to see this, but if you've done it, I'm open for business. All right. So yeah, I'm probably going to, if there's any part of the talk that I might sacrifice a little bit of specificity on, unfortunately, it's going to be the active volume architecture. I'll try to focus on the stuff that's important towards our compilation pipeline. But yeah, I would encourage questions here, but I'm sorry if I have to, in the interest of time, say that, give a quick explanation and move on. Because there's a lot, this is a very rich subject, of course. Okay, so here I'm just going to give a slight overview of the things that I'm going to use for the people that recognize the terms. If you don't recognize the terms, that's fine. But I just have to say this out loud for trying to mitigate a few questions that might come up. So active volume is an architecture that is geared towards photonic quantum computing, but we often see it in other places. In fact, yesterday, I think some Googlers came up with an architecture that I feel is strikingly similar to active volume. So I feel that this is actually a quite widely applicable architecture and therefore is worth spending all of your time on today. One thing that this really takes advantage of, at least in the case of photonics, is this sort of switching, which allows us to quickly reroute qubits and get them close to each other. I'll talk a little bit more about that later. In this particular talk, I'm going to talk about using lattice surgery, although the active volume architecture is not limited to lattice surgery. The point of this active volume architecture is to reduce idling and more efficiently pack operations, reducing idle time on your memory. So that's really the advantage here, is this efficient packing that can help you to decrease the total space-time volume of your calculation and therefore the total time. And lastly, I'll go over this briefly later, is that we use fiber as a short-term memory. So you can store a photon in fiber, and the amount of photons you can store in a fiber of a certain length essentially determines the size of your computer. So yeah, extremely high-level overview. Let's just talk about service code as you all know it, right? It's just some plaquettes that, some combination of contrasting colors. Our fusion graphs look quite similar, where instead of having a single sheet here, we arrange our photons in layers here, where in each of these dots that you see in this diagram is what we call a resource state. It's just a 6 photon state that we prepare through some some proprietary process. And we perform 2 qubit fusion measurements to sort of glue them all together into this big lattice, which we can compute on. And of course, do lattice surgery on, because you can just fuse different pieces of the lattice together in order to perform lattice surgery. Turns out you can implement this thing with a fairly easy to understand gadget that I encourage each of you to go into the active volume paper and attempt to work through yourself. But the crux of this is that you have this resource state generator here that generates all of these resource states. You have photonic switches, which basically tell the photons where to go and what to fuse with. You have these fusion devices. And lastly, we have these delays that I was talking about before. And it's these delays that really determine the size of your quantum computer. If you can stuff more photons into the fiber, you can get a bigger lattice and have more logical qubits. And that's an important thing. One other important thing to note is that in the normal implementation of a surface code, you would require 2 d² qubits, right? Where 2 of those qubits are used to extract syndromes. In our case, you just need d² resource states. So some of you might expect to see a factor of 2 in these resource estimates. They will be absent. Okay. Do I need to? I can skip this one. Let's save your time for more interesting things. So, okay, I'm just going to go through a brief, I'm going to use the next slides to briefly go over how depth 3 resource estimates occurred previously in the active volume architecture. And this will hopefully inform us a little bit as to how we're going to use the depth 4 resource estimate provided by the deeper compilation. So as you can see, we have our total number of qubits n, our total number of logical qubits n on our right-hand side. And this basically just says take the number of interleaving modules, that's those little squares that you saw before, multiply them by the amount of photons you can store in the fiber. That gives you the total number of resource states you can keep alive. Then you divide that total number of resource states by d squared to tell you how many patches you can get. And that gives you an estimate for the total number of logical qubits in your system. Yeah, and as you can see, you have some length of your delay, and the time, the speed of light in fiber basically determines how many of those photons you can stuff into that individual interleaving module. So, OK. So we have an estimate for our total number of qubits. What do we do with it? Well, we have to consider how we can use those qubits to perform lattice surgery. Each of these lattice surgery, oh no, am I out of battery? No, OK, requires D syndrome checks for each logical cycle. And in each logical cycle, we can perform one of these, like connecting two of these patches, as you normally do in a lattice surgery operation. We describe these operations using ZX calculus diagrams that look something like this. So here's an example of how to implement a Hadamard gate in active volume. You can see like input rails and output rails as you would in a normal ZX diagram. But these hexagons and red dots and stuff, they're basically just bookkeeping to make sure that each one of these lattice surgeries is a valid operation in the active volume architecture. So there's a lot of nuance that goes into making these diagrams that we will ignore today. We're just going to say that, like, OK, for a gate like Hadamard, it's got 3 of these blocks, and we're going to schedule them. We've got to figure out a time when they're going to occur. And that's all we're going to worry about today. But just know that there's like some deep stuff going on there. It's like how these things are created. OK, so what we normally do in the depth 3 resource estimates is we partition our qubits into 2 spaces. Half of them are memory, half of them are workspace. The letter W will determine the size of your workspace, or will represent the size of your workspace. And what we assume is that you can essentially perform swaps on each of our gates. And these can simply be done by rerouting fiber. So if you're storing qubits in a certain fiber, you can reroute them from one part of your computer to another. And this allows you to make qubits that were previously far from each other now close and can do lattice surgery on each other. So I'm not going to go too in depth as to how this occurs. Just know that there's plenty of time in order to do this, because typically if you have a distance 30 surface code, you'll need 30 syndrome checks in order to do a single logical block. That's 30 of these quick swaps that you can do. And for basically a computer of any early fault tolerant size, this essentially allows you full rearrangeability at each of your logical cycles. OK, this is an important slide. So I want to tell you about this trick from active volume. I don't know if it's from active volume, but we use it gratuitously, called bridging. Sorry, seem to have accidentally. There we go. OK, so essentially what this bridging technique allows you to do. Oh, Chris?
Mind if we go back a slide?
Yeah, of course.
Just a quick question, which was, so you say there's a logarithmic number of connections. It's log base 2, right?
Yes.
So if we have like 500,000 qubits, isn't that like 19 connectivity? That seems pretty high, right?
500,000 qubits.
Is it logical qubits?
Oh, sorry, logical.
Yeah.
Oh, sorry.
Yeah.
Logical qubit,
Sorry.
then we should be on the order of 10, right? Connections?
Yeah, usually that's pretty feasible.
Can you give some insight into why? Like when I hear 10, I get really worried, right? Because I see a lot of like atomic platform, for example.
Yeah, so this isn't coupling in like the typical like superconducting sense or like atomic sense. This is just rerouting photons in fiber, right? Which only requires more options on your switch in order to do. And of course, you got to pay for more fiber. But you know, which is a thing to consider. But you know, it's much easier to purchase fiber than it is to plan out you know, a new connectivity range. So keep in mind, we're not doing any entangling with these things. We're just doing some swaps, right?
So I should just think of it as like a switch box, and it has just like 10 ports.
That's literally what it is.
Okay.
Like at least in a photonic way. It's basically a switch box. Yes, it's a photonic switch box.
So does each of these connections store one logical patch?
Yes. So it's like each of these blocks is one logical patch.
And you say you're storing them in the fiber, right?
Yes, you can use fiber to both direct and store, right?
I see. Like, do you have more logical patches in one fiber each time?
Yes, and I will wait 2 or 3 months to hear more from me on that. But for now, we'll just assume that we have like one interleaving module per patch. That's probably the easiest thing to do for today. But there is a way to get that done. But yeah, unfortunately, not the focus of this talk. Any other questions? Yeah, you asked a very deep question, and I look forward to answering it in a paper fairly soon. Okay, moving forward. We are a little bit past halfway. That is perfect. Okay, so we have this technique, which is super duper important for the active volume architecture. We have basically what is called bridging, and it allows us to execute operations in parallel that were previously in series. This is super useful because it allows us to take advantage of all of the workspace that we have much more efficiently. So previously, let's say we had to do these in series, right? If B is very small, you might have to wait for B to finish and have all of your workspace just idle while B is being executed. And then if A is big enough to hold the whole workspace, then maybe you don't sacrifice as much. But if you can fit them both into the same logical cycle, you can save a lot of time. The price you pay is you have to introduce another qubit, which we call a bridge qubit. Previously, it was thought that you had to introduce 2 qubits, like you would pay a 2-qubit cost. But it turns out that you can use one of these bridge qubits to compute on A. And so the cost actually turns out to be only 1 qubit, which is maybe a little bit less than what people were thinking previously.
So here you kind of assume the time cost for like wait and apply A is kind of smaller than like apply X and that and do measurement and do the feed forward operation.
So I should mention that yes, in the active volume architecture, these sort of Bell measurements are very cheap. You can do them in a single code cycle or a single syndrome extraction. And these like X prime and Z prime are just Paulis, so we track them, right?
Are there restrictions on what kinds of operations A and B can be?
Nope. Even like non-Cliffords, you can make an argument that like you can do this pass through. It just turns out that you have to flip whether or not you apply the correction. So if you previously didn't, you now might have to, and if you previously did, you might not. Yeah.
What X prime and Z prime?
They're Paulis that basically they're just Paulis that are used to correct your system. If you want, I can go to a little bit more into depth as to how this works after the talk.
Wait, can I just go back to what Peter's asking? So in the case where like B itself has a correction in it, is that a case? How does this play out in this case?
Well, in B, you don't have to.
You can't do it in this.
No, you can. If B has a correction, you don't really care that much, right? Like you just do B normally. It's only if A has a correction that you have to like flip whether or not, because these Paulis only commuted through A, right? Not through B.
So when A and B are non-Clifford, are X prime and Z prime still Paulis, or are they?
Yeah, turns out that you just like. Yeah, can I talk about this after? Basically, all you need to do is in your magic state injection, you just flip whether or not you. Okay, so let's say A is a T gate, right? And you got to commute an X through it, right? Then you'd pick up a factor of S, right? But happy day. Normally, you just have to apply a correction of S when you do a T, right? So all you do is flip when you apply that correction, and that is sufficient to essentially commute the X through a T gate. Hopefully that was a good enough explanation, but unfortunately I can't dwell on this that much longer. If you want, I'd be happy to give you an explanation afterwards. Okay, any more questions?
A and B doesn't need to commute.
No, that's the cool part, is that A and B do not need to commute. You just pay this extra cost in bridging.
I think I didn't fully follow the correct argument. So I see how you're saying that the thing that would matter is if A requires, say, S correction. So, yeah, where does that show up in this diagram?
Well, you would absorb it back into A. Really, A becomes like an A prime that applies the S correction in the opposite way that A would, and the opposite times that A would. I know this is maybe something that I probably should have spent more time on and not swept under the rug, but I might need to come back to it after the talk. But trust me, bro, it's fine.
And this scales past 2 operators?
Yeah.
So you're saying if I have something which would be nominally depth n for an extra n qubits, I get depth 1?
No, you get depth 1 in the Clifford operations. Because remember, we're counting lattice surgery operations here, and those are essentially just like Clifford operations. You still have a reaction depth to deal with, as Chris was asking before. You will see that taken care of later on.
So why do you only require 20% qubits to be the bridge qubits?
Oh, yes. That is a great question, and we will get to it. Turns out, that's not a great assumption. And it's one of the things that we test in our paper. So previously in the active volume paper, yes, we did assume that like we allow for 20% extra memory to account for this bridging cost, as well as like things like autocorrect states and stuff like that. But we test this hypothesis and show that maybe it diverges from reality. Yeah, any other questions before we move on? Cool. Yeah, so this is another kind of important slide. So previously, we only talked about workspace and memory. And we added an extra 20% to the memory just to take it, just to account for these like bridge states and stuff like that. But now we're going to split up memory into these like bridging states. There's data qubits, which is literally just the qubits from your circuit. And then there's going to be stale states, which are the autocorrect states that Gidney often references. And of course, we have some that are going to end up unused, unfortunately, at each round. Thankfully, it turns out to be a small number. I saw the hand go up for a second, Chris. That's OK. But yeah, we sort of have each of these roles for each qubit. And the point of our depth 4 resource estimation is going to be assigning each qubit one of these roles at each logical cycle to make sure that we are accounting for how qubits are used in our computer. Yeah, this is the depth 3 analytic resource estimation. Yeah, you can do this. You can read the paper. It's not super important. I'd rather talk about the stuff that I did, which is the block scheduler. I shouldn't say it's just me. You know, me and my colleague Sam Heavey worked very hard to make this block scheduler a reality over the course of like maybe a year or so. So the first thing we do, as I'm sure Kevin will tell you, is we create a DAG to represent each of our operations in our circuit, our directed acyclic graph. So here's like a kind of toy example where we have operations A, B, and C, right? And we convert them into nodes. And if like A and C don't commute, then you draw an arrow between A and C. And because like B commutes with everything, it has no arrows to anything. It's just like some free node in your graph. And we use this for 2 things, right? It clarifies when bridging is needed, right? Like if you want to do A and C in the same logical cycle, you're going to need some kind of bridging in order to do it. And it also shows where these reactions are required, right? If 2 things don't commute and they have non-Cliffords in them, you'll need to account for a reaction in that particular node. Yeah, this is stuff that has been covered before, so I'm not going to. Actually, maybe I should.
What's the starting point of the circuit? Do you assume it's unitary or anything, or it's like you have an arbitrary circuit with measurements?
So.
And you still make it DAG, or?
So if you have classical feedback, you get some loops in your DAG, so it's no longer a DAG. But it's still basically a DAG, so I'll call it a DAG. But
any like Clifford plus T plus measurements of classically controlled.
Yeah, anything can be put in this form. Yeah, but like I said, it's a little bit, you fudge it a little bit, but I'll call it a DAG anyways, because that's what the classical people do.
How does the feed-forward become a loop?
Sorry, there's like feedback, like if you had repeat until success. Sorry. No, feed forward is more like you'd have to wait on one of these to execute a stale state. Yeah, Kevin?
Yeah, so I understand A and B commute, but they act on the same qubit, so don't you need some extra resources to do them in parallel?
Yes. And that's quantified by, great question, Kevin. So we keep track of what qubits each one of these act on in each node. I know it's too small to read, I'm sorry. But if we see that, okay, these guys got 3 qubits in common, we're going to need to bridge 3 times in order to execute them in parallel. So we take that into account.
Well, even between A and B, though, which you don't have anything in the DAG.
Oh, yes. Well, we track,
so you're just
that's regardless of arrows, right?
Okay.
We need to bridge them, yes. Yeah. Any other questions? Amazing. Okay. So we have this memory and workspace combination that I was talking about before, and we're going to, as I mentioned before, at each logical cycle, we will assign the total number of unused qubits in our computer to one of each of these categories. Now, the first one, we're going to do it basically by 2 principles, right? We're going to try to minimize the number of bridge qubits, right? Because bridge qubits, they're not really doing anything to help us compute. And the second thing, we're going to try to unlock the most operations, right? So that'll make more sense in just a second when I give you an example. So let's take a quick example of this being done. Let's say we have 7 unused qubits in this particular example. And in each of these nodes, we'll have the total active volume of the operation that's being executed. So we got 1 big guy over here, right, and 2 smaller guys over here. So you notice you have way too much active volume to be executed in this particular logical cycle on this node. So we'll move on to the other 2 in this round, right? And we'll say that okay, we're going to execute these 2 in this logical cycle. And now we only have 2 unused qubits, 3 unused qubits left. And we still have way too few qubits to do this 80, so we're going to have to do a bit of bridging, right? So when we do this bridging, we have to pick from each one of these 3 operations here and figure out which one is the best to schedule, right? So if we're going to pack in this first guy in the logical cycle, if it shares 2 qubits in common with this operation that you're already executing, then you're going to need more bridging. So we're going to eliminate that from our possibilities. Next, we're going to go for nodes that unlock the most other nodes to complete, right? So that's going to be the one on the left because more other nodes depend on it. So we come down to our last node, and we finish our logical cycle by executing that node right there. So that's the basics of how it's done. Let's say that magically in the next round you have 80 unused qubits or something, right? Now we have enough to take this big guy over here, right? And we'll say that 80 active volume blocks. This thing is big enough to require a stale state. In other words, it's required an autocorrection state. And when that happens, we will, in the next logical cycle, require however many stale states there are to idle in the computer. So basically, in the next logical cycle, they won't be doing anything because they'll essentially just be decoding. And of course, if you have a depth greater than 1 in a particular logical cycle, then you will have to wait multiple times in order for each of those reactions to finish. Thankfully, we find in our work that the reaction depth in each logical cycle never exceeds 1, or extremely rarely exceeds 1. Yeah.
So are you fixing the number of logical qubits available at the onset, or are you deciding that on the fly?
We are fixing the number of logical qubits at the onset, and we want to allocate them to certain tasks. Yes. Of course, some of them will be used to hold data. I'm just talking now specifically about how we're going to use the qubits that are not already holding data at the beginning of our logical cycle, or planning our logical cycle. Great question. Any other ones? Because now's the time, because this is kind of the crux of the talk. Afterwards, you're just going to get a lot of pretty pictures.
Question. So the input that you take to generate the DAG, you've compiled it already into those in that particular form. And I guess there's a lot of choices there. But for your work, you're saying we have that, we've done it in a way that seems good, and we're going to schedule it.
Yeah.
Okay.
But you're right to say that that is a non-trivial process. It is, in fact, the slowest part of our compilation pipeline. Thankfully, you don't have to repeat it every time you change your code distance because the operations are the operations, and they just their dependencies are the same regardless of the code distance.
Yeah, but like if that 80 qubit thing could have been broken up into 40 qubit like that, yeah.
Typically, this is an excellent question. Yes, typically we tend to favor operations that have smaller active volume, and that allows us to more efficiently pack operations into a given logical cycle, right? So yeah, this is maybe a bit of a change of pace of what I thought when I first came to PsiQuantum. Like when I first came to PsiQuantum, I knew about active volume, and I was like, okay, let's make these huge diagrams. We're gonna, decrease the overall active volume of the total computation down as much as possible by combining operations into big things. Turns out, maybe that's not the best thing to do, right? Maybe we want to consider smaller operations that can more efficiently fit in a logical cycle instead. And I feel like this is one of the core learnings from this work. So thank you very much for the question. Chris.
Is it easy to assess the active volume of operations given that you have the geometric constraints on boundaries, on the exposed boundaries of your surface code patches?
Yeah, I wouldn't say it's easy, but you can do it, right?
So doesn't that also mean that you have to... Well, let me ask a separate question actually first then. If we were to try to apply this technique to other platforms without quick swaps, right, it would degrade because there's a lot of communication overhead that's incurred, right? So is that also part of the calculus here, is that you can move things around quickly and so that the active volume can be somewhat stabilized?
So in this particular definition of active volume, yes. I have a strong suspicion that active volume can be applied in more cases where in the routing itself is the active volume. I think that's what we were starting to see in the Google paper.
I was wondering, can you predict how many unused qubits you're going to have?
Yes. We just track all of our qubits in each round, and that you know exactly how many you have.
No, in the future, you're going to make some choices. And then...
No, this is strictly greedy, right? We're not worrying about saving qubits for a rainy day here.
Because maybe you will never have 80 available, and you have to wait. You have to, not greedily assign stuff to do your big node.
So what happens if we have a size 80 and we don't have 80 qubits to give? It fails. It just says, I can't compile this, try again later.
Okay, but then as an alternative, maybe you can start with 40 qubits and then bridge to the future to do another 40 qubit computation.
Absolutely. You could try to break up this 80 qubit thing into something smaller. Yeah, this is a pedagogical example, right? It's not something that actually appears. But we do get things that are sized 35. That's about as big as we get.
When you say it fails...
a quantum out-of-memory error occurs.
And you have to restart from scratch?
Yes.
Oh.
Yes.
Yeah, that sucks.
Yes. I mean, that's why... Okay, but this is a great point. Because remember that flowchart that I was talking about before in the very beginning of this talk? That flowchart is designed to try to minimize the number of quantum out-of-memory errors you get. In fact, you'll at most see maybe one or two at the end of the day. Because if you start with a good guess as to what the error correction strength is.
So I would assume this, in your example, 80 means, you've taken some big block and said it needs active volume. Would you, break that into smaller things then in the case? You go to this question of okay, I want to trade space for time in this case, right?
Yeah, absolutely. And we had to do things like this in our, in the course of our creating this scheduler, right? We, at the beginning, had some fairly expensive operations that we were like, wait a minute, this isn't working. We should break them up into just regular old C-naughts rather than a huge network or something like that.
Yeah. So you could break it up. So all these twos are just supposed to represent C-naughts or something like that.
Yeah, basically, or something cheaper. I just pick numbers here, right?
I understand that, but the question is about how complex that block is. That block, the 80 block, is a bunch of stuff, right?
Yeah.
And you're saying that.
You can break it up usually.
Yeah, so is there a strategy then in the long term for minimizing the likelihood of there being any number greater than 0 of these kinds of failures in a given run so that you don't dominantly limit your algorithm success rate with this type of failure?
No. Basically,
sounds dangerous.
No, I mean, okay. So what I'm telling you right now, or at least I try to mention that like you don't get these very often if you have a good guess as to what the distance is. And you can use a depth 3 resource estimate to get a good estimate of the distance, and so you don't have to compile more than 2 or 3 times. Yeah.
Just to clarify, this is a failure like in your compilation step, like you don't worry about it happening once you've compiled it and you're ready to run.
Oh, yeah, we're not talking about compiling in real time
Well,
here.
that helps.
Yes,
Thanks.
yes.
Thank
Thank you.
you.
Okay, he was thinking about compiling in real time.
Correct.
Yes, no, I'm not wasting QPU hours by like not breaking up my
Yeah.
operations properly. That's going to cost a lot of money.
That helps.
They would not be happy about that.
Wait, so is it true that also, so say if we just make this a little more concrete, let's say like the 80 volume thing is like the Gidney adder subroutine.
Something like that.
Twos are like, the small ones are like C naughts, just
Sure.
because of that hypothetical.
Mm-hmm.
So I guess one scenario, if you didn't have a workspace of size 80, you could say like, all right, maybe I shouldn't use the Gidney adder subroutine. I should just decompose it into like C naughts or Hoffmans or whatever. Is it also the case that you could just take the Gidney adder subroutine, which itself is made up of like a bunch of blocks, and do bridging to schedule them, to fit them into a...
That's a tough question. Sam Heavey, my partner in crime on this, would have more to say about that. There are some clever things you can do, but nothing that can be applied generally as far as we know. Any other questions? In fact, I think I'm going to hold all questions till the end because I want to show you my pretty pictures. So I showed you this thing, right? Look at this. Okay. So I got a big U here, right? We're going to test it out in a Fermi Hubbard controlled unitary, right? And I'm going to talk about this controlled unitary, and here it is being scheduled. So as you can see, each of these red dots in the diagram slowly become green. Each of these yellows represents a stale state. And you can see the DAG going from left to right, showing the general direction the computation should proceed in. Yeah, pretty cool, right? Like, you can actually see one of these compilation pipelines working. And of course, each of these layers down here is like, I do a longest path layering of my DAG. And you can see the operations being scheduled in it. I'm sorry, I know you probably have a lot of questions. I'm sorry. I might have to hold off because there's some other cool graphs I need to show. So here is the usage of each qubit, each logical cycle. As you can see, for like an early fault-tolerant application, for like a 4x4 controlled unitary, we are dominated by data qubits. And I expect this to be the case for basically, if you remember, data qubits are just all the qubits from the circuit itself. We expect them to dominate the qubit count for basically all NISQ operations. We also have active volume, which is just the workspace that I was talking about before. And as you can see, all the other like stale states, bridging, and unused, they're less than 10%. They're a very small portion of the computation, as promised. One last thing that I really wanted to do here was show you that, like, okay, remember that 20% of the memory that we were dedicating towards bridging and unused and stale states? Here's what it looks like for the 4x4 Fermi Hubbard across different sizes of computer, right? And as you can see, this yellow line, which is the previous model, basically inverts the actual model that we found. So it turns out that perhaps a new model for how to execute how much of your computer is taken up by stale states and bridging qubits is perhaps warranted. But good news is we have the model now, and you can ask me about it later. Yeah. Also, I compare it with basically a previous resource estimation method from, I have this paper, Bliss THC, and I use a resource estimation method in there. I compare it to it. Basically, it's like almost half the time. And because you can decrease the time, you can decrease the distance. Because you decrease the distance, you can increase your number of logical qubits that you have with the same amount of hardware resources. Yeah. That's it. So here's a summary. Depth 4 resource estimate, basically a tool for active volume architecture. And future topics, let's do depth 5.